conversation talking points. Okay? So here we go. We got a lot of stuff to go over. And the math today is not hard. The math today is not hard. We just need to get some theories down that we can really build upon. Okay. So, what we're looking at today is absolute max, or I'll just go maximums, minimums, or just another word, extrema. I don't know if there's two M's in extrema or not. What do you think? One?
I'm looking at it.
You're looking at it. Okay, good. Okay. I've never claimed to be a great speller. I'm getting better though as I grow up a little bit. So absolute max or minimum. Okay. So what we're talking about here is, so what I'm going to do is I'm going to write the technical definition, and then we'll throw a picture at you to try and clarify it. Okay? So, function f has domain D. Okay? So domain is all the different numbers we can plug in. All of them. That might be a limited set. It might be an interval, an open interval, might be a closed interval. We don't know. Okay? It's got an absolute max at C if and only if f of C is greater than or equal to f of x. And I'm going to give you a notation that the book doesn't even give you for all x that belong in my domain. This symbol right here, this little E thing, that means is an element of, or that are in. Okay? And that should be pretty straightforward. It's an absolute max, which means bigger than everything else that we can plug in our domain. Kind of duh, right? Okay? So it's an absolute min at C if, what does if with two F's mean? If and only if. Good. Okay? If f of C is less than or equal to f of x for all x in my domain. Okay? Let me get my pictures ready. Okay? So on the most part, it's not too difficult to understand, but there are a couple little hiccups that might give you grief. Okay? Like this one. That's got an absolute minimum, but it doesn't have an absolute maximum because it goes on forever and ever and ever. There is no point for which you get a larger value than everything else. Okay? Here, we have an absolute minimum and an absolute maximum if we just do it on the closed intervals 0 and 2. So we can use 0, we can use 2. When I plug in 0, I get the smallest of anything I would ever get. If I plug in 2, I would get the biggest of anything I would ever get. Okay? This one here, what if I'm doing an open interval, 0, 2, so I can't use 0. So I can use 2, so I've got an absolute max. But what do you think about an absolute min? Do you think I have an absolute min? I would not. Because I could always get closer and closer and closer and closer and closer to 0, and it would always be smaller. And there's no final value that I could ever plug in that would be the smallest, since I don't have that endpoint. Okay? So this one here, does it have a maximum?
No.
No. Does it have a minimum? No, not at all. Some of you guys might be thinking, wait a minute, that's its highest point right next to it, but what's right next to 2? 1.9? 1.99999? 1.999999999? there is no magic number that's going to get results that are bigger than all of the rest. Okay? And again, if anything in here gives you grief, let me know. Okay. Let's do some more. This one is, I don't know if the names are important, really. This is called the extreme value theorem. Okay. So, my domain is some closed interval from A to B. Okay? So, there is some x of 1 in my domain and x of 2 in my domain, such that f of x of 1 equals some m, and f of x of 2 is some big M. Okay? I'm just going to write it and then we'll come back and explain it. So that m is less than or equal to f of x is less than or equal to big M for all x in my domain. Okay? And my domain specifically, I should probably say the closed interval A to B. Okay. So what this is basically saying is that when you have a closed interval, there's always going to be a highest point and there's always going to be a lowest point. Okay? And it's going to be at a couple different possibilities, which we'll come back and talk about a little bit later. Okay? So, let's take a look at some graphs. If I'm looking at this interval, actually, any interval, there's a highest and a lowest point. So this is the value of x, and they're calling that x of 2, where my maximum occurs. Okay, and this is where my minimum occurs. Same thing here. There are values. This one just happens to be at its endpoints. Does it have to be at its endpoints of interval? No. Okay, but there is, as long as it's a closed interval, there's a highest and there's a lowest. There's a highest and there's a lowest. Okay? So, not a big deal. Okay? At least I don't think so. Other points we're interested in are local extrema. Sorry. Local extrema. Okay? Okay. There's a local max if f of c is greater than or equal to f of x for some interval containing c. Okay? So it's a local maximum if it's bigger than everything else in some interval. Okay? Who's the tallest person here besides me? Jesus. Okay? So, Jesus is our local maximum. Okay? But are there classrooms he'd be in where he wasn't the local maximum? Yeah. Okay? Shortest person, Willa, are you the shortest person? Could there be classrooms where you are the local maximum? If you go down to third grade. No, I don't mean that. I'm just saying, I'm not saying you're short. I'm just saying, I'm just saying, I didn't want you to think about all your classes and this, that, and the other. I'm just saying, we could have a situation where you're the local max. Okay? But it just depends upon the neighbors that you have. Okay? Again, I wasn't calling you short. Okay. And anyway, I think height is just a trait. It's not a flaw necessarily. Okay. It's got a local min if f of c is less than or equal to and on the same thing. Okay? So basically it just means there is some area of the graph where at C there's a value that's higher than the ones around it. Okay? So if I take a look at these graphs, okay, look at all these different types of minimums and maximums. This one's a local minimum, no greater value of f around it. So if I pick this interval from, say, from here to here, then it's bigger than all those. Okay? Same thing here. That's a local minimum. This is a local minimum. Okay? Because it's in that interval, and I can use that point because we'll say that the interval includes that endpoint. This one's an absolute maximum. How come? On the whole thing. Okay? This one's absolute minimum because nothing's lower on the whole thing. So while this is tallest person in your class, shortest person in your class, this is tallest person in the school. This is shortest person in the school. So I don't think that's a greatly huge problem. Okay? Now this next one, I think you guys can figure out. What do you notice about these extrema that I have circled? Think about what we've done before, what we've spent a lot of time talking about. We've talked about slope. What's the slope right there? 0. What's the slope right there? Yeah. What's the slope right there? What's the slope right there? 0. Okay? So this is a really important idea. They actually call it Theorem 2. Okay, come on, pencil. Okay? Basically says f prime of c equals 0 if f prime of c equals 0. Well, I should probably state it the other way. Okay, hold on. I'm going to erase this. I'm sorry. Okay, if there is a local max or minimum at C, then f prime of C must be 0. For it to have a local max or min, then the slope has got to be 0 at that point. Okay? Has to. No other choice. No other choice. And you know what? We are surprisingly close to being done. Oh my goodness sakes. Okay? And then this is very important. If f prime of c equals 0 or f prime of c is undefined, then C is what's called a critical point. Something is happening at that point. Okay? That's a critical part of my graph. No doubt about it. Okay. So, let's go like this. Finding absolute max and minimum on an interval. Okay? Well, here's what I want you to think about. if I've got some interval, let's just say a to b. I don't know if I draw this. I'm just trying to clarify. If I have something like this, where could my max and min occur? Yeah, it'd be at my endpoints. Okay? Do my max and min have to be at my endpoints? No. I could draw something different, and I could say, here's a to b, and I could go like this. Okay? It could be at any other point. Okay? What kind of point is this? It's a max, and it's actually a critical point. It's a critical point because my slope is 0. So here's the deal. How to find, look at that, finding has a G, Rex wrote. Nice job. Okay, wow. So they're going to occur at the endpoints or at critical points. Okay? So here we go. Today, we're going to do this problem. We're going to find the absolute maximum minimum of this interval. We're going to do f of x equals 4 minus x squared on the interval from -3 to 1. Okay? So here's what we have to evaluate. We need to evaluate the endpoints. F of -3, what is it? F of 1, what is it? And we also need to evaluate it at any critical points. Okay? So how do we find our critical points? Well, it's a critical point if my slope is 0. So I got to have this, and I got to differentiate it. So I'm going to say f prime of x equals -2x, right? Okay. So now what I've got to do is I've got to set that equal to 0. Can't believe I actually showed that. And I get x equals 0. You got to remember I teach a couple different levels of class. So I've got to evaluate that point as well. Okay? So you're going to do an endpoint, all critical points, and then you're just going to find what's the biggest and smallest. It's that straightforward. So f of -3, I get -5. F of 1, I get 3. F of 0, I get 4. Please double check me. Okay. So I'd say it's, what? Yes, because I'm trying to find out, this is not f prime, now I'm looking for the height of my original function. That's one of the things that's going to get confusing as we go back and forth. Sometimes we're interested in plugging into the derivative, sometimes we're interested in plugging into the original. On this one, think about we want the height of the function, not the slope of the function, we want the height of the function. So we're going to go back to the original. Okay? So here's the way I like to state this. It's got a max of 4 at x equals 0. It's got a minimum of -5 at x equals -3. Done. Okay? Are there problems that the derivative is going to get a little bit more complex? Yeah. But we'll do some more examples with that tomorrow. But I think for what I'm going to give you guys today, I think you guys will be able to get through this pretty quickly. You are correct. Okay? Okay, so here we go. Here's what we're going to do. We are going to do page, where's my notes? Page, I don't even have the page number written down, 272. 1 through 14 all, and then 15 through 19, just the odds. 1 through 14 all, that's going to be pretty straightforward. Okay? 19. 15 through 19. Yes, ma'am. Ooh. Okay, so you're going to find your derivative, and then it's just that solving your derivative equal to 0 would be more difficult. So say if this was a cubic, then our derivative would be a quadratic. So we would have to factor, or we'd have to use quadratic formula to find the values of my critical function. Which there's not going to be a lot of that, so don't worry about it. Okay, but like Tay alluded to, if it's sine or cosine or secant, then that's where we're going to have to spend a little bit more time. Great question. Okay, no, you don't need to explain. Just go, it has a max, but no min. Or minimum and no max, or it has both a max and a min, or stuff like that. Yep. 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 Yeah, you don't have to explain how your answer is consistent with theorem 1. I'm fine without that.